Hey guys, it's Jimmy here. Today I want to talk about vector analysis. It's all about mathematics. The reason why I do that is that when personally myself is studying electromagnetics and field theory, there are a lot of vectors calculations involved in it. And I was really struggling with it at that time because there are a lot of rules and vectors about directions and space in three-dimensional space, and it's very hard for human brain to sometimes to imagine some of the calculation in your mind, um because it's 3D and your brain is kind of struggling to do so, and you need some rules, but um the rules are very complicated, and also you don't know how to prove them. So at that time I was very struggling, so that's why I made this episode, vector analysis for physics students. I try to simplify everything down, and I also listed some useful properties you can use in probably in your learning while you're learning electromagnetics and field theory. Okay, so I made episodes in total. The first one, which is this one, is about inner products and outer product, and also the differentiation of vectors. Okay, let's start. So the first one is inner product, and its definition is given as follows. A dot product B is equal to the modulus of A times the modulus B, and times the cosine value of the angle between the two vectors. Okay, so obviously it's modulus times cosine value, so it's a scalar. That's what we should note here. It's a scalar, and that is one of the major differences between the two operations, dot product and cross product. Okay, so let's see if it has any geometric meanings. Okay, so A times the modulus A. Okay, I draw a little diagram here. Here's vector A and here's vector B, and this angle is the angle between them. So B times the modulus of B times cosine theta, which is the angle here, times is equal to this length. This length right here, which is exactly the projection of the vector B along the direction of the vector A. So it's basically like the modulus A times B's projection on the direction of A. A hat means on the direction of A, by the way, for the notation. Also, if we break it down into Cartesian coordinate system, the dot product actually means ax. The ax means the vector. I wrote right down here. It means a's component along the x direction, x-axis, and b as well. So similarly, okay. So basically, it's like ax times bx plus ay times by plus az times bz. Okay. So what we can what we can and we can make analogy here, because we are very familiar with vector addition. A plus b, for example, is equal to ax plus bx, and ay plus by, and then cy plus cy. So basically the purpose of dot product is just he changed this plus sign to the time sign, so the rest remains consistent. Okay, so it has a distributive property, which means that a dot product, the sum of b and c, the vector b and vector c, is equal to the dot product between a and b and plus the dot product between a and c. Okay, of course we can use the second property here. You just prove it algebraically, but actually we can also prove it using our using its geometric significance. Okay, I drew a diagram here. Here's vector A, here's vector B, and here's vector C. So on the left side, we have the vector A times the sum between the sum of B and C. Okay, so I drew a parallelogram, of course, because you want to add these together, and these two are the equal. So basically, it's just this segment plus this segment, and it will point toward that direction. So this green arrow here is just sum of vector B and vector C over here. Okay, now we want to prove it's equal to a times the dot product between a times b. So remember the geometric significance. Basically, actually, both all the three terms here all begin with the modulus of A. So actually we can just simplify this to this to the sum of BC, which is the sum of B and C, which is this arrow, is this its projection on A, which is this long arrow here. This one. This is called B plus C's projection on A, the direction of A, and this shorter, a little bit shorter arrow here, this one is actually, if you look at the big picture, it's actually the B's, the vector B's projection on A. Okay, so this is B's projection on A, direction of A, and so C is here. So this the shortest vector here is C's projection on A. So what we want to prove here is actually this short segment plus the second longest segment is equal to the longest segment here. So actually it's kind of easy. We just need to prove that this segment here is equal to the difference between these two segments, right? Okay, so since it's a parallelogram, you can easily find the congruence between the two triangles, which are here and here. So basically we have, since the parallelogram we draw here, so this angle is equal to this angle, and since and this this side is equal to this side, and this angle is equal to this angle, and of course, since all of these are parallel, this angle is equal to this angle, so ASA. So these two triangles are congruent, means this side is equal to this side, and since here is a rectangle here, so this side equal to this side. So problem solved. We've already proved it. Okay, so that's like I find this way of proving the distributive property of dot product it's easier to memorize. Okay, so here's inner product. Inner product is just a scalar, so it's kind of easier compared to a cross product, which is also called the outer product of two vectors. Okay, now we move on to our outer product here. So as I just mentioned, the outer product of two vectors is not a scalar anymore, it's a vector. So how to determine its direction first? We use the right hand rule. So here's how it works. So first you pull out your right hand, and if you can let you point your right hand in the direction of the first vector, which is vector A here in this case, and then you curl your fingers to make your forefingers toward the direction of the second vector, the vector B here. So if you can do that, and the direction of your thumb will give the direction for the cross product. And if you can't do that, if you tried first, then you need to flip your hand and try again. If you can eventually do that, the direction of the thumb will be your answer. So that's how to determine it. And that's so as you can see here, the direction of the cross product is perpendicular to both of the two vectors here. That's the special point about it. So now after we figured out how to determine its direction, we now need to learn how to determine its modulus because it's a vector. So let's check the definition again. The modulus of A times the modulus of B times the sine value of the angle between them. So actually the modulus of A times the sine value, you can see is equal to the height of the parallelogram spanned by these two vectors. So if you times again by the modulus of B, which is side length here, you will automatically get the area of the parallelogram spanned by the two vectors, which is the shaded area here. You'll get its whole area, and that's its geometry significance. Okay, so this is how we can determine it if we draw a diagram. So what if we can't? Just like if it's complicated, we also have an algebraic way to determine the modulus of the vector, which is by using determinant. The first row of the determinant here is actually which is ex, ey, and ez are unit vectors in the Cartesian frame. Unit vectors in 3D Cartesian coordinate. Okay, so and we just expand this expand the first row, and we'll get the following expression here. So and as you can see, we have already taken. We can know the components of the cross product, in the three directions: ex, ey, and dz, and we will find that, it is kind of cyclic. Okay, I'll introduce what is cyclic here. So let's see. All these properties we talked about is under the right-handed Cartesian system, which means, which has the x y z axis, just like they're put in this kind of sequence x y z, not x y z or x y z, or this kind of weird things. It just put in this order. And under this order, we can find that the cross product between ex and ey is equal to ez, and this equation holds true under cyclic permutations. What is cyclic permutation? It means that if we change x into y into z, and z into x, this formula holds true again. Like, for example, we cyclic one time, and it becomes ey times ez, and the value is equal to ex again. So that's what cyclic permutations is. Okay, so now we just talked about how to compute the value for the cross product using the determinant, and we obtain this expression. Also, actually, the cross product has distributive property as well. This expression here, you can't also as well. One more time, you can prove this property by just violently break all these down into the Cartesian frame and use direct computation. Like, if you write it out, you will get the expression like, left side is equal to, because it's a cross product, it's determinant ex ey ez, and ax ay az, and b plus the sum between b and c, which is bx plus cx, by plus cy, and bz plus cz. You can do that by directly computing this determinant, but it involves a hell of a lot of calculations. So using the geometry significance, we can also prove this property. Look at here. So on the left side, we have the cross product between the vector A and the sum of B and C, which is exactly the area for this big red little parallelogram here. Okay, so we need to prove that this area is equal to the sum of the area of this parallelogram and the parallelogram spanned by A and B. And that's the thing that you're trying to prove here. How to prove that? Okay, first we set the vector A as the universal base. Actually, because we're timing the modulus of A every time. So we set this as a universal basis, and we drew the heights. We use a purple pen, and so this is the first height, and the second height is here along C, and the big height is here. So what we need to prove, again, we simplified it into we need to prove this height plus this height is equal to this height, right? Okay, here's how we're gonna do it. First, we extend this. We'll get a rectangle here, right? This is a rectangle, so this is equal to this. So now what is left is this segment. Here we must prove this segment is equal to this segment. Then the problem is finished, right? Okay, then how are we going to do that? Recall that we use the congruence of two triangles here, because we have parallelogram and a lot of parallel lines. So actually, similarly, we can apply the same method. It's not hard. All we need to do is extend this one more time, and you draw another height. So you can see here, this is a rectangle here, and so this length will be equal. Let's change the color, orange. So this side will equal to this side. Now we can use our intuition. We can see that two triangles seem to be congruent, which is this triangle in orange and this triangle here. If they are indeed congruent, then our problem is solved. Because if this is equal to this, then this will be equal to this, and after adding up the two heights, the problem will be solved. And how are we going to prove this congruence here? It's easy as well, because we have got a lot of parallelograms. You see, since this line is this segment is equal to this is parallel to this segment, and this segment is parallel to this segment here, this whole segment here. So this angle, so this angle is equal to this angle, and equal to this angle. Okay, so we have one angle now, and so since this is a parallelogram, this side will be equal to this side, right? We have an angle and side. And now the third condition here is this is since it's a right angle triangle. So basically, we just need these two conditions. That's enough. So these two, we have already proved that these two triangles are congruent, and this side equal to this side. So it's problem solved. We have proved that the area of this parallelogram plus the area of this parallelogram is equal to this red parallelogram. Okay, so we have already successfully proved our distributive property. So actually, that's not hard at all. We just need to connect this with the geometry significance of the operation. Okay, now we will move on to other properties of cross product. Since actually you can, as you guys can see here, the cross product is more harder than dot product. So we want to want to do is actually break down the cross product into dot product. So, and that can make the problem very, much easier. So that's why we came up with the first property. So the cross product of between B and C. Okay, now I want to move on to the other properties of the cross product. Since cross product is harder than dot product, so what we want to do is to break this to transform cross product into dot product. So okay, so the first property here, this can be very useful, because it involves three vectors cross multiplying each other, and that will be a mess if you just compute it directly. So the formula we use here, we just change it to the difference between two vectors. So let's first actually, if you want to prove this equation, you can again substitute all these components into A, B, and C, and directly obtaining the equivalence, and that's a violent way of doing it. And we also can do it elegantly. Like, first we need to understand it. First, in the bracket is the vector B cross product vector C. So its direction will of course be pointing in a direction which is both perpendicular to vector B and vector C. Let's draw a little diagram here. So B is here. Let's for example, if B is here and C is here, so obviously A will be pointing directly perpendicular to both of the vectors. So, and after, sorry, not A, it's B times C. So if if the vector A cross product this vector here, like for example, A is over here and it has the angle between the two, it will again point toward the direction of B and of the plane in which vector B and vector C are in again, which is this shaded plane. Why? Because the product again will be perpendicular to the direction of the direction perpendicular to B and C. So that cancels out each other. So the product will be again lies in a plane between b that lies in a plane spanned by vector b and vector c. For example, like here, that's in the plane. Okay, so after, and we can figure out some extreme cases to determine the exact form of the product. Since we have already figured out that it must be some type of coefficient between in front of b, plus or minus some coefficient times the vector c, because that's how we make sure this that's how we make sure that the vector is will lie on the plane spanned by b and c. And let's think about two cases. One is b is parallel to c, so the angle between b and c will be zero. Right? And that's how we make the assumption. And after we substitute this condition in, because if the angle between b and c equal to zero, the product between b and c will be zero as well. So and vector a times cross product of zero again will yield zero. So the whole answer will be zero. Okay, so that's our first assumption. And let's see our second assumption. If the direction of a and the direction of c is equal, and both of them are perpendicular to the direction of b, and we substitute this condition inside, we'll get that and the answer for both of the expressions is equal to the direction of the b. And after considering these two cases, we can obtain our expression here. So that's how we figure out the formula intuitively. Okay, so after we have this formula here, we can know that since the expression is cyclic, so meaning that if we change from a to b, b to c, and c to a, the expression will hold true again. So the sum of these all the cyclic permutations of this expression will equal to zero. This is very useful, and this is called Jacobi identity. It's very, very, very useful. Okay, so here's our first property. The second property is this. Remember what we defined for the algebraic computation for the cross product? We have this determinant, and after we change the unit vectors here in the first row into the components of a vector ax, ay, and az, and we compute this determinant, we'll get this expression. And after analyzing it, we'll find that it's the dot product between vector a and the cross product between the vector b and vector c. So we'll get this result. So the determinant have such a property that if you swap for an even number of times any rows or columns of determinant, the result will stay the same. I mean, this will stay the same. Meaning that if it holds true for all its cyclic permutations will be equal to each other. So using this identity, we'll get this, and it can simplify mixed. You can see it's a mixed calculation between dot product and cross product. And when I learned about vector analysis, I find this kind of expressions the most annoying. So I listed here. So I think can help you guys. And then we use another property of the determinant, which is determinant of AB is equal to the determinant of A times the determinant of B. So if we use that property, we can get this, and we can convert a large mixed calculation between 6 vectors into a determinant, and the determinant will be much more easier to compute. Okay, and anyway, to conclude the auto product part, we just we can use our geometric significance to prove some things. If it doesn't work out, you always have the algebraic way of solving things. Just violently turn it into a determinant and calculate it. So, and that's all. Okay, so the last part is about differentiation. So the differentiation part, you can all just prove them by just expanding them in the Cartesian coordinates. You include the components ax, bx, ci, ax, ay, az, bx, by, bz, and then substitute all this inside. And since the derivative of unit vectors, like for example, ex over something over something like dx or dt is always equal to 0 because the unit vectors are consistent and they remain still and unchanged. So it will always be 0. So we're just calculating the coefficients or the components or the components part, and we can yield all these results. So what interesting about it is that for vector r, which is which for vector function r, which is a function of x with constant magnitude, its derivative is perpendicular to it. We can prove it. Since we dot it with itself and equal to r squared, it's a scalar, and the derivative of a scalar over the x is equal to 0. So the first part is equal as well, and we expand the first part using our rule here for dot product, and we'll get 2 times the vector r times the derivative of r over dx, and we'll get that this is equal to 0. Meaning that this part and this part is perpendicular to each other. Get this. This is very important for kinematics if you are using, for example, in circular motion, and we're talking about velocity here. So if, for example, circular motion, we draw a half circle, we draw a circle here, and for example, the velocity over this side, there's some mass point at this location and the velocity at this side. You know based on your knowledge that the acceleration will be pointing to the center, and here's why. It will always be the derivative, because a is equal to the vector the acceleration vector is the derivative of the velocity vector, and so the two will be perpendicular to each other. So, and that's why. And so this is the first episode for vector analysis, and I hope it can help you guys.